This is the final block diagram. This is the clock and its divider, which all sequential logic in the processor only takes place when it changes from 0 to 1. The program counter keeps track of the program. For branch operation, 4 is added to the counter, and the immediate value is left shifted by 2 and also added to the counter. For jump operation, the counter is left shifted by 2. For other instructions, we consider the counter is incremented by 4. The instructions are stored in the ROM. The register file contains registers and which can be loaded to get a value or store a value. The ALU do arithmetic and logic calculations. The result of the ALU can be passed into the memory as an address and store the value on the data bus at that location. The display driver is only enabled for the address of FFFF1 and FFFF0, and the memory is enabled. It displays the value on the data bus. If the branch operation is called and the ALU is doing subtraction and the result is 0 and the branch control is 1, the program is branched to another place of the code.
Multiplexer. This is our single-bit multiplexer. A multiplexer has 3 inputs, 2 data inputs, and 1 select input. When the select input is set to 1, the output will be the same as the data input D1, and if S is set to 0, the output will be the same as D0. So we can select each of the data inputs depending on different situations. And this is a 4-bit multiplexer. The 4-bit multiplexer is simply consists of 4 single-bit multiplexer. They have 2 4-bit data inputs, and they share just 1 select input and gives 4-bit data outputs. And then we will be able to build a 32-bit multiplexer. Sum extend and shift left. For sum extend part, we take any value which is less than 32-bit long. In this case, it's a 60-bit data input, and we extend it to a 32-bit data output without changing the actual value it holds. So the highest 60-bit data of the data output depends on the 16th bit of the data input in this case. If we run the simulation, the highest bit of the data input is 1, so the output, the highest 60 bits will still be 1. And if the highest bit of the data input is 0, they will be all zeros. For the left shift part, we simply shift a data input to the left by 2 bits. And by doing this, we multiple binary data by 4. These two stuffs can be used in our single cycle processor. We can use them to extend and manipulate some intermediate code or the jump code. ALU. This is our ALU. We have 2 32-bit data inputs and a 3-bit func code. The func code will decide what the ALU will do. Our ALU can do A and B, A and not B, A or B, A or not B, and it can also do addition, subtraction, and the set lesser. In this part, the 3rd bit of the func code will decide if we take B or not B. For not B, we will do the logic involving the not B, and we can do subtraction. And in this bit, that is a logic bit, we can do AND or OR depending on the 1st bit of the func code, and the bottom part is the adder. So the func code, the 3rd bit func code again decides if we do the addition, in which case we give the carrying 0, or the subtraction, then we'll give the carrying 1, and the result of the addition or subtraction will go to this multiplexer, and this bit is the set lesson bit. The subtraction result will be used in this zero extent, so we'll look at the highest bit of the subtraction result. If that is 1, then A is of course less than B, because the subtraction result is a negative number. Otherwise, A is greater or equal to B. Then is the final multiplexer. We will decide if we do the logic part or we will do the addition and subtraction. That is decided by the second bit of the func code, and then we'll get the final output of the ALU.
The main decoder of the control unit. It is calculated based on the table. The input of the main decoder is the opcode of the instructions. The outputs are register write enable, register destination, ALU source, branch, memory write, memory to register, 2 bits of ALU opcode, and jump, which all controls a single bit in the processor. For the 6-bit opcode, by observation, the most significant bit is always equal to the least significant bit. The first bit is always 0, so we calculate the combinational logic between the digits 0 to 4 in the input and outputs using K-map. Here's the result. This is the simulation of the main decoder.
ALU decoder switches between 2 constant values depending on the least significant bit of ALU op, switches between that result and the combinational logic result depending on ALU op's most significant bits. The combinational logic uses the least 4 significant bits, and I used 4 separate Karnaugh maps to draw out what would be the outputs for each of the bits. So bit 0, or index 0, index 1, index 2, index 3, and that outputs a 4-bit bus. The most significant bit of that 4-bit bus is always 0, so it's kind of arbitrary. Finally, we take those least 3 significant bits, ignoring the 4th index, which is always 0, and that gives us the ALU control signal, which is the output to the ALU decoder. So this is the program counter, which is a 32-bit register of memory. It takes in the clock pulse from the system clock, and it takes in a 32-bit data bus. The reset input is active high, and it resets all the values to 0. I built this up using 4-bit registers, 8 4-bit registers, and this is the simulation for some random values. We reset it first, and that brings the output to 0. When the data bus has a non-zero value, and it's a rising edge in the clock, we then have the valid output of this. We have the same output as the input of the data bus, and as we continue on, anytime the data bus changes, the value of the data bus changes, and we have a rising clock edge, the output also changes accordingly. The 4-bit register was created from 4 resettable flip-flops. The resettable flip-flop was created by adding some reset logic, where it's D and not reset, into a standard D-type flip-flop. The D-type flip-flop was created from 2 D latches, and when it's a 0 in the clock, it'll pass into the middle section the value of the data, and then when you reach a rising edge, it'll pass into the output queue. The D latch was created from a set reset latch that just sets the value of D when D and clock is 1, or resets it resets the set reset latch to 0 anytime the value of the data is 0 and the clock is 1. And at the lowest level, we've got the set reset latch, which is just 2 NOR gates.
This is the display driver. Its inputs are 1-bit clock, 32-bit address bus, 32-bit data bus, 1-bit enable, and 1-bit reset. The outputs are 7 segment displays. If the address input bus is equal to FFFFFF0 and the display driver is enabled, the 32-bit register is now enabled and the data bus gets stored. Bit 0 to bit 24 of the data bus gets displayed to the 7 segment displays. If the address input bus is equal to FFFFFF1 and the display driver is enabled, the flip-flop is now enabled and the least significant bit of the data bus gets stored into the flip-flop. If the least significant bit is 1, the 7-segment display gets switched off.
Okay, this is the program to display the squares from 1 up to 100, so display 1 squared, 2 squared, 3 squared, up to 100 squared on the LED device. We begin with the initialization, where we have a register, the main counter register, we set to 1, using the addition instruction, because since the 0 register plus 1 will always be 1, because the 0 register is always 0, and we set that value to be stored in T1 register. Then similarly, we'll use that to set the maximum value that we want to display into the register T2. Then on line 6, we begin the main loop, where first we check that T1 and T2 aren't equal, so we haven't reached the maximum value yet. If we have, we will branch to reset. We can discuss that later. So we have a temporary T3 variable. We're going to use it as a variable. So we first set it to 0 and assign 0 to T3. Then we also have a counter, sort of a variable, and we store 0 into this counter variable as T4 register. We're going to use this. The T3 will be used as the actual squared number, and T4 will be used as a counter to make sure that we add it the correct amount of times. So we begin the add loop. First, we will add the number from T1 to the number that's going to hold to the register that will hold the squared number, which is T3. And then we'll increment the counter so that we keep track of how many times we've added it. If we reach the number of times that we needed to add it, and if we have, then that will be, the counter will be equal to T1, since we need to add a squared number n amount of times if the number is n. And so if we reach that, we'll exit out of this add loop and display T3 onto the LED, which will be the squared number. Then we'll increment the main outer counter, T1, so we'll display the next squared number for the next loop. So we jump back to the main loop. Eventually we'll reach eventually T1 will be equal to T2, the maximum number that we want to display, and then it'll branch into this reset loop, and then we'll reset block, and it will set T1 back to 0 plus 1, which is 1. We'll jump back to the main loop, and it will keep repeating.
This program displays the number in a Fibonacci sequence from 0 to 10,946. A Fibonacci sequence is a series of numbers that, starting from the third element, its value equals to the sum of the previous two items. Initially, we set the number stored in register T1 into 0, which is always the number stored in register T0. Same for register T2. Now it comes to the loop. We store the number in register T1 to the memory, and this number is also displayed onto the display driver. Same for register T2. Then we compare the number stored in register T1 to the number stored in register T3. If they are equal, then we branch to reset. Same for register T2. Now they are not equal, so we continue. We add the number stored in register T1 and the number stored in register T2, and the result is stored in register T1. We add the new number stored in register T1 and the number stored in register T2, and we store the second result in the register T2. Here we got two more Fibonacci numbers. As we're going back to the start of the loop, the two new register numbers got displayed, and we are producing new Fibonacci numbers. As we are going looping around, and finally the number stored in register T1 or the number stored in register T2 is equal to the number stored in register T3. Now we are branching to reset. At reset, the value stored in register T1 is set to 0, and value stored in register T2 is set to 1. Same as what we did in the initial part of the program, so the program starts again.